Okay. So, we have seen that this S2 value is 7397.9 kVA, that means roughly 7398 kVA, and here the transformer capability is 7200 kVA. Therefore, the capacitor installed to improve the voltage regulation are not adequate. Therefore, additional your capacitors is required. Now, in the second case, the new power factor required can be found as that cos theta 2 new, right, is equal to P upon S T. P we know 6942 kilowatt and S T is 7200 kVA. Therefore, it is 0.964, right. So, new power factor. Now, thus the new required reactive power can be found as that Q new, this is actually Q new, is equal to P tan theta 2 new. So, that is 69 P is 6942 into tan and cos it is inverse theta 2 new, right. That means cos theta 2 new you have got it 0.964. So, theta 2 new is cos inverse whatsoever, you put these values here, right, you will get Q new is equal to 1910 kilovar, right. Therefore, we know Q new is equal to Q minus QC, it is ADD means additional capacitor, that is QC add is equal to 1910. Therefore, QC add is equal to Q is equal to 2556.8 and minus the 1910. So, it is coming 646.7 kilowatt, that means this amount of additional amount of var required, right. Now, this economic justification for shunt capacitor. Now, I will tell you this, but when all these things will be completed, I will explain each and everything later. First is that economic justification, first it release generation capacity. What does it mean? I will come later. Release transmission capacity, that also I will tell you, right. Then release distribution substation capacity. Then number 4, additional advantages in distribution system, A, B, C, D, E, F, 4, 6 things are there. One is reduced energy, that is I square R loss, it will reduce voltage drop and consequently improve voltage regulation. This is also because of the shunt capacitors effect. Release capacity of feeder, because it will draw because of shunt capacitor, that feeder will draw less amount of current, we will come to that also, although something I have explained on this. Then postponement or elimination of capital expenditure due to system improvements or expansion. I think this is happening because of the distribution substation capacity release, right. And if you put capacitor, then feeder may not be overloaded. So, that your what you call expansion or your what you call that your of the distribution system or improvements you can defer by few years. Then revenue increase due to voltage improvement. If voltage improves, then naturally energy meter reading will be higher, right, because it will then that is the thing, right. And another these A, B, C, D, actually these 5 your what you call advantages for under distribution system, other 3 regarding the generation and transmission side, but when I will come to the end all this point I will take and I will explain how is it, right. Now, example with shunt capacitors, right. For example, suppose we take the same data, same 4 bus example. This is bus 1, bus 2, bus 3, bus 4. Voltage is here substation, this is slack bus, it is 1 angle 0, V2, V3, V4. Suppose we have connected a shunt capacitor at node 3, right. So, although here for the calculation this IC actually is not required, but still I am showing that QC being injected and corresponding current is IC, and this capacitor value say we have taken 400 kilowatt, right. Therefore, and these loads are already given, this is 400 plus J 300 kVA, this is 500 plus J 400 kVA, and this is 600 plus your J I have missed, here it is J 400 kVA, right. That is 400 kilowatt, 300 kilowatt, 500 kilowatt, 400 kilowatt, 600 kilowatt and 400 kilowatt. When you put every 2 things in bracket, they are in kVA, and this impedance is also same, it is in per unit, right. Z1 is 0.7442 angle 30 degree per unit, Z2 is equal to 1.4456 angle 22.16 degree per unit, and Z3 is equal to 1.96 angle 22.56 degree per same impedance, and a capacitor is connected. Now, if you have connected a capacitor here, there is capacitor injecting power, then what will be the effective load here? It will be 500 plus J 400 minus 400, that means here it will be 500 plus j 0, because this is this kilovar part is being compensated by this shunt capacitor, right. So, if you for your understanding what I have done, I have made another equivalent diagram of this one. So, in that case this is substation, again everything is same, but here at node 3 that this capacitor is connected, therefore, it is 500 plus j 0, because this one is totally compensated by this one, right. So, in that case your and for this one what we will do, we will use only the first method of the load flow. Second method I have not done it here, but I request you can check also using the second method. So, then you compute the current for I 2, it will be voltage, flat voltage start, that means all the voltages initial values are taken 1, that is V 2 is equal to V 3 is equal to V 4 is equal to V 1 is equal to 1 angle 0 degree per unit, right. So, all the node voltages V 2, V 3, V 4 are taken as their slack bus voltage. So, flat voltage start, and so in this case this I 2, I 3, I 4, I 2 and I 2 we have initially calculated, it is P 2 minus your P L 2 minus J K L 2 upon your V 2 conjugate, but all the initial values are 1 angle 0. So, this is actually your I 2 is equal to 0.005 angle minus 36.87 degree per unit. So, that is 0.004 minus j 0.003 per unit. Now, I 3, in the case of I 3, now it is actually P L 3 minus j Q L 3 upon V 3 conjugate, actually effectively Q L 3 here is 0, this is the equivalent diagram. So, Q L 3 is not there. So, basically it is 500 this has been converted to per unit divided by your 500 kilowatt divided by 1000, it will be megawatt divided by MVA base. So, basically 500 by 10 to the power 5 into 1 angle 0, because it is 1 angle 0 this V 3 conjugate or V 3 same, because angle is 0, right. So, if you compute, it will become just 0.005 angle 0 degree, that is 0.005 real values for this case, and I 4 is equal to same as before. So, it will be you convert it to per unit, divide by 1000, it will become megawatt, then divided by MVA base, same as before, and similarly you will get I 4 is equal to this, already we have calculated when we are solving that load flow, right. Same data, I have taken same data throughout this chapter. So, I 4 is equal to 0.0072 angle minus 33.69 degree, that is 0.006 minus j 0.004 per unit, right. This is I 4. Next what you have to do is you calculate the branch current, that is I 1, I 2, I 3. I 1 will be equal to your I 2 plus I 3 plus I 4, the small I 2, small I 3 plus small I 4. So, I 1 is equal to I 2 plus I 3 plus I 4, the small i's, right. So, you add this is your I 2, this is your I 3 and this is your I 4. So, if you add, it will become 0.015 minus the 0.007 per unit, and its magnitude will be 0.16553 angle minus 25.017 degree. Similarly, I 2 is equal to I 3 plus I 4, I 2 is equal to I 3 plus I 4, right. So, I 2 is equal to your I 3 is this much, and I 4 your what you call I 3 is your this much 0.005 and I 4 is this much. So, it is coming actually 0.011 minus j 0.004, that is I 2 is equal to 0.0117 angle minus 20 degree. So, and I capital I 3 is equal to I 4, because this is the last node, I 3 is equal to I 4. So, this is the last node. So, I 3 capital I 3 is equal to small I 4, that is 0.0072 minus 33.69 degree, right. Up to this all the branch currents are computed. This is first iteration, I am not writing an iteration number here, when second iteration will come I will do that, but these are all first iteration, right. Then V 2 is equal to then V 1 minus I 1 Z 1, substitute V 1 value, then I 1 value, then your Z 1, Z 1, Z 2, Z 3 all with same value all in per unit. So, it is actually coming V 2 is equal to 1 minus 0.012318 angle 5 degree. So, if you multiply and simplify all these things, V 2 actually coming 0.98773 minus j 0.001073. So, this is actually 0.98773. So, angle minus 0.62 degree, this is V 2 in the first iteration only, right. So, similarly, V 3 will be V 2 minus your I 2 Z 2. So, similarly, V 3 is equal to V 2 minus I 2 Z 2, right. So, it is 0.98773, that is V 2 minus j 0.001073, I mean this V 2. this V2 right. So, minus your I2, this is I2 and this is Z2, all these things are known. So, just simplify right. So, you will get basically after simplification all these things you will get V3 is equal to 0.97083 minus j 0.00171. So, this is magnitude is 0.97083, but angle is minus 0.1 degree. Look here, because of the capacitor, earlier when capacitors was not there, although this angle is very small, but it was coming leading angle, but as soon as you have put the capacitor, look this angle is a change, it is lagging angle now, although very small, but lagging angle. Similarly, here also V3 if you look, it is minus 0.1 degree, but it is your what you call it is a lagging angle right. And if you talk of compute V4 is equal to V3 minus I3 Z3. So, V3 is this one minus your I3 is this one and this is your Z3, multiply and simplify all these things, then what you will get V4 is equal to 0.956984 plus j 0.001014, it comes around 0.95698 angle 0.06 degree. Here it is leading angle, but very small, but leading angle, but other two is your coming lagging angle right. So, all these calculations whatever I have made by calculator, I request you when you will go through this lecture video lecture thing, please verify whether I am right or wrong. If you find any mistake in calculations, you just please let me know. Now, question is that last voltage angle, it has become actually here on this first your what we call after first iteration, this voltage angle become positive because this is 0.06 degree, but here these two are becoming your negative, lagging this thing right. So, in the explanation I told you something, but that does not mean that it depends of course on the capacitor value, but I told you that wherever you connect the capacitor, shunt capacitor, from that point to the source right, it will be affected only this. Affected means that loss reduction will occur only in this branch and this branch for this example right. And whatever your what you call that voltage drop or your minima your whatever current it was drawing without capacitor, and because of this capacitor this branch current and this branch current will be less, but here I3 will remain more or same because as it is connected at node 3. So, beyond this node any node are there, it will not be affected, whatever little bit because of this capacitor this voltage will improve, because of the improvement this voltage also to some extent will improve right. But your power loss at this branch reduction will be just only due to this voltage improvement, but that magnitude will be very less. But here your first thing is the current will reduce, because if we take I2 is equal to ID your what in this diagram previous diagram, suppose in this case if current is say branch 2, say ID2 plus minus JIQ2 and this IC is injecting. So, your imaginary component of the current or reactive component of the current will decrease, therefore, voltage drop will be less. So, voltage will automatically improve. Here also it will decrease, but this I1 is higher than this one for this example say, that means your reactive component of this one is higher than this one, but as soon as this IC is coming here also it will be subtracted from the reactive component of the current, but whatever reduction of here will be much more compared to this one, because this reactive part is higher than this part. So, loss reduction also will be here, but compared to if you take the same resistive values, then compared to this one it will be here reduction will be more, here reduction will be less if you assume same R right. But anyway it depends on the your resistance as well as reactance of the branch right. So, this is your what you call that V2, V3 and V4, and this is your after first iteration. So, next if we move to the second iteration. So, after first iteration these are the voltages, V2 is given whatever you have got it, V3 is given and V4 is given. These two are lagging angle, although angle is very small and negligible, but and this one is leading angle. Now, second iteration we will now see in second iteration we have to compute the your what you call that load current of small I2, small I3 and small I4. So, second iteration the small I2 will be 0.004, that is the load PL2 minus JQL2 upon that V2 conjugate right. So, it is V2 is equal to 0.98773 angle minus 0.62, its conjugate will be this angle will be plus right. So, it will be 0.98773 angle 0.62 degree. If you simplify, if you just simplify, then I 2 will become 0.005061 angle minus 37.49 degree. So, if you is equal to, it is I 2 is equal to 0.00401649 minus j 0.0030809. Similarly, I 3 is now only PL because QL has been compensated. So, this one divided by your V 3 conjugate. So, V 3 we have got it 0.9708, the angle was minus 0.1. So, its conjugate it will be 0.1, and you simplify, it will become 0.00515 angle minus 0.1 degree, because here is nothing means its angle is 0, because here is no reactive part. So, its angle is 0, right. So, it will be minus 0.1 degree. Now, if you simplify, this part is negligible actually, it is 50898 because of this one. So, real part is dominating, right. So, I t is equal to 0.051499 minus this j 0.50898, this is actually you can neglect, right, it has no effect. So, I 4 is equal to now your P L 4 minus j Q L 4 upon your V 4 conjugate. So, in that case your what you call this one I 4 previous page, just hold on, previous page, I 4 is equal to V 4 conjugate is minus, actually it is minus, right, it is conjugate means it is minus, right. So, your if you just make this your what you call this calculation or your I 4 is equal to, so it will be coming your 0.0075352 minus 33.6. This, although this is by mistake it is written minus, but I think this angle is taken correctly, right. So, in this case, so this one is equal to, it is 0.006274 minus j 0.004173, right. So, with this now your what you call that capital I 1 is equal to I 2 plus I 3 plus I 4, sum up all the currents, right. Then you will get the second iteration, the branch current, this is your second iteration, right. With this you will get I 1 is equal to, after simplification you will get 0.017059 angle minus 25.16 degree. So, similarly, capital I 2 is equal to small I 3 plus I 4. So, this is your, this part actually negligible for I 3, right, but still I have written here plus this one your I 4, right. If you make it simplify and make it, it will become 0.01216 angle minus 20.66 degree. Similarly, capital I 3 is equal to small I 4 is equal to 0.0075352 angle minus 33.63 degree, right. So, this is all I 1, I 2, I 3. Even I will suggest you for faster calculations, at least for this example, the voltage angle actually very small, this voltage angle, right, all these voltage angles are very small, this one, all these angles are very small. So, even if you neglect this angle, directly if you take the voltage magnitude, you will get a quicker solution and very close to the actual solution, right. So, now in the second iteration V 2 is equal to V 1 minus I 1 Z 1. So, put at the 1 angle 0 V 1 and put all this value in the second, and this is your Z 1, this is your Z 1, and you simplify. If you simplify, you will get V 2 is equal to 0.98735 angle minus 0.062 degree, right. In per, these are all per unit, these are all per unit, all calculations, even if I have not written, because again and again, but these are all per unit values, right. Similarly, V 3 will be is equal to V 2 minus I 2 Z 2. So, that is actually 0.98735 minus j 0.0010711 minus this is your I 2 and this is your Z 2 values, right. You just multiply and simplify. If you multiply and simplify, V 3 will become 0.96978 minus j 0.0015311, that is actually 0.96978 angle minus 0.09 degree. Similarly, V 4 if you compute, it is equal to V 3 minus Z 3, right, and this value of V 3 you put it here, you are putting it here, this value of V 3, right, and then minus your I 3 into your, this is your I 3, this is your Z 3 and this is your I 3, right. So, if you simplify all these things, then it will become actually 0.95528 angle 0.078 degree per unit. This is that after second iteration, this is the voltage magnitude, right. So, this is only when you are taking capacitors, therefore, just see the comparison. This is After second iteration, this is with shunt capacitor, right, this is with shunt capacitor. So, after second iteration V 2 is 0.98735, here it is 0.98578. So, there is a slight improvement, I mean because it is a small system. So, voltage improvement is here because it is 578, it is 735, right. Similarly, that your without capacitor it was 0.96590, this we have seen it when we are doing the load flow method of the first method, right. Only from these results are taken from the first method after second iteration. So, here it is 0.96590 angle 0.36 degree, here it is 9590, it is 0.96978. So, voltage has improved. Similarly, this one it is 0.95137, but here it is 0.95528, here also it is improved. So, everywhere voltage actually has improved, and because of the capacitor, although not all the time it will happen, but for this example this angle was leading, here it is lagging, here it is leading, here it is lagging, here it was leading, here also it is leading, but there is some change in the angle also. So, this is your what you call that after second iteration the voltage. Now, whenever we put shunt capacitor, so we expect that power loss will be less, that there will be less power loss. So, after second iteration only I will ask you that you should make third iteration and see suppose at third iteration you will find solution has almost converged. So, I will request you to make third iteration and check this. So, this thing I have told you that net power injected at the substation, already I have told you, that is P s minus j q s is equal to V 1 conjugate I 1, that is V 1 is equal to 1 angle 0. So, V 1 conjugate is also 1 angle 0. So, basically it is equal to I 1. Therefore, P s minus j q s I 1 is this much after second iteration, this value is after second iteration, right. So, P s is the real part of this one. So, 0.01544 because this is in per unit megawatt. So, multiply by base MVA 100 I have multiplied, then you 1000 I have multiplied. So, all this thing it is coming 1554 kilowatt, right. Therefore, P loss will be, this is that power injected at the substation I have told you, minus that sum of all the loads. So, 400 kilowatt plus 500 kilowatts plus 600 kilowatt, these are node 2, these are node 3, these are node 4. So, ultimately loss is coming 44 kilowatt. So, when we are taking without capacitor that initial load flow studies, that using this method it was coming 57 point something it was coming. So, but here it is 44, that means loss has decreased due to the shunt capacitor placement, right. Similarly, Q loss is your similar way you find out this is your Q s is equal to actually 0.00725339 pu. So, that you multiply by 10 to the power 5 because 100 MVA base and 1000, right, in terms of kilowatt because you want to have kilowatt. So, basically it will be 725.39 and reactive load will be your node 2 and node 4 because 3 is compensated, right. So, basically it will be 300 plus 400 700. So, it is coming 25.39 kilowatt, but original one I think we got 26 or 27, but here it is reduced because at the same time line reactance was also your what you call less compared to the resistance. I mean if you take R by X ratios, right. So, here also reduced, here also loss is reduced. So, this is your what you call that your shunt your what you call that using of shunt capacitor is that loss reduction is very significant, and that is why I told you again and again that sometimes we feel that shunt capacitors perhaps it improves the voltage level. No, the basic idea of shunt capacitor is is that its objective is to reduce the power loss, that is a primary objective, right. Right. The secondary objective is though not much, it improves the voltage level, right. It improves, but although it will be not like series capacitor, but whereas this ones your shunt capacitor it actually reduce the power losses in the network. So, if you go to any substation anywhere, particularly you will see although it is there on the 33 kV side or 66 kV side also it may be there, but in distribution system also you will find that utilities all over the world they are putting shunt capacitor, at least 2, 3, 4 shunt capacitors are putting. For that they try to find out the best location. Just you have a distribution network, say 120 nodes distribution network or even large distribution network, and there just arbitrarily you cannot put shunt capacitor, then instead of gaining you will be loser also, loss may increase also, because if you put in not an optimal place, So, in the classroom exercise I cannot teach you that optimality and other things, but I will tell you at the end of all these things that how one can do optimal thing. And if you have a load flow program, you can easily make it, you at least using analytical method. So, this is what that shunt capacitor, where it is that loss reduction is the significant in shunt capacitor, right. So, this is regarding shunt capacitor. Now, if for the same example, just for the purpose of your understanding, what I will do, for the same example I have taken a series capacitor also, and in the case of series, this is the same example. I have written R1 X1, R2 X2, R3 X3 just to show that series capacitor somewhere in distribution line connected, but same Z1, Z2, Z3 value will be used, identical thing throughout this thing, just to have a feeling that same parameters are used, right. Now, what in the case of series capacitor, I have made a series capacitor connected in branch 3, that is here only, right. So, that means it is given minus Jx3. So, this is the current, this branch is I1, this is it I2, right, and this branch current is I3, right. So, question is that these loads are same, 400 plus J 300, 500 plus J 400, 600 plus J 400, but there is no shunt capacitor at all. When you take the series capacitor, rather than kilovar, you have to consider that your reactance of the your what you call that series capacitor. So, because that if you take QC3, it will be basically I square X3. If load is changing, I will change, the Q will vary, right, it acts like a voltage regulator. So, in that case, in that is why this X3, this R1, this is R1 X1, R2 X2 and R3 X3, right. This all these thing you take in per unit, then XC3 also you take it per unit, because it is in branch 3, that is why it has been taken. So, from the common sense it suggests that if we put capacitor here, then voltage of this node will improve, because for this branch reactance will decrease, because it will be R3 plus J X3 minus XC3. So, because of that reactance of this branch will decrease. So, V4 voltage will increase, but in this side that V2 V3 it will not be affected that way, right, because it is connected here. So, before proceeding to this, I will suggest you, when you will take this problem, you put the say capacitor here, whatever value I have taken, you put the capacitor here, then you will see voltage of this node will increase successively, 3, 4 all the voltages will increase, right. So, that was but just for your understanding I have taken here this your XC3, and there you will also see that I1 I2 there will be not much change, even I3 also there will be not much change in the current, but voltage improvement will be there, but it is a very small system. So, I cannot guarantee a large improvement of voltage, but if you take a realistic network, right, I mean which are network which are your physically your what you call existing, those network if you take and you can verify this. But let me tell you, in distribution system that your series capacitors are not being used due to some reason, but you have to see this, right. So, these parameters, that R1 X1, R2 X2 and R3 X3, these all are in per unit, and same parameters are taken, same loads are taken for your understanding. So, in per unit I am writing PL2 is equal to 0.004 pu, QL2 is equal to in terms of per unit 0.003 per unit. So, PL3 is equal to 0.005 per unit and QL3 is equal to 0.004 per unit, and PL4 0.006 per unit and QL4 is equal to 0.004 per unit, and substation voltage V1, this one is 1 angle 0, and what your voltage this voltage is V1, this voltage is V2, this voltage is V3 and this node voltage is V4, right. So, and Z1, Z2 and Z3, Z1 is same value 0.7442 angle 30 degree per unit, these are all per unit, right. I have not written, but throughout the thing we have written all per unit, right, all per unit, and Z3 is equal to 1.8106 1 point, because Z3 here it will decrease, because earlier it was your here it was your X3 is equal to 0.758, but X3 we have taken 0.70 say per unit we have taken. Therefore, X3 minus XC3 it will become your 0.052. So, Z3 it has decreased earlier I think it was 1.89, now it is 1.8106 angle 1.6 degree, right. Thank you.